Hello, and welcome to the second day of Unit 13, Intermolecular Forces, and how that relates to solids and liquids. So today what we're going to really focus on is how intermolecular forces of attraction, which make solids and liquids and gases happen, especially with nonpolar or with covalent molecules, how we can change those molecules from solids to liquids and gases by overcoming boiling points and melting points. So let's kind of get to the first slide. And while you're getting to the first slide, I'm going to sort of talk about the most common phase or state change that people think about, which is water. Water, when it is a solid, is ice, melts. When it melts, it becomes liquid, which we call water. And when we boil it, it becomes a gas, which we call steam. And that's the most common one that people think about. So a melting is defined as when a solid changes phase or state into a liquid, and boiling is defined as when a liquid changes phase or state into a gas. The thing that's common about all of these things, about both melting and boiling, is that energy is added. However, if we wanted to freeze something or if we wanted to condense something, we would take energy away. So what's the relationship between intermolecular force strength and melting and boiling? Well, the greater the melting point, or the stronger the intermolecular forces of attraction, the more energy is needed to overcome the intermolecular force and cause that change of phase or state. Long story short, the higher the boiling point, the more energy is needed to make that liquid become a gas. So you could pause this here and copy this down, and then we'll go on to the next example now. Okay, so here we have two substances that happen to have the same technical chemical formula. It's really C2H6O. So I've got two carbons, I've got 6 hydrogens, and I've got 1 oxygen. So the chemical formula is the same. But because of how they're arranged, they have two very, very different boiling points. So let's talk about what the structure is and why that makes them significantly different. So for the structure on the left, what I have present is I have a covalent molecule. And because it's a covalent molecule, the very, very first thing that I can automatically tell myself is that London dispersion forces are present. Okay. I see that there is some dipole stuff present. So I see that there is a carbon-oxygen bond that appears to be somewhat polar. So I'm going to check. So I see that 2.5 minus 3.5 is equal to 1.0. That's my electronegativity difference. So yeah, there's a little bit of polarity there. And that little bit of polarity tells me that there is some unequal distribution of electrons. But because this is pretty much a nonpolar molecule, because the molecule itself is pretty symmetrical, I would say that there's a small amount of dipole-dipole. And then lastly, the one thing I want to take a look at is there any HF or HO or HN bonds present? And I would say that there's definitely not. So that tells me that there's no hydrogen bonding. Okay, now looking at the molecule on the right-hand side, I see that the molecule on the right-hand side is a nonpolar or is a covalent molecule. And right away, that tells me that I have LDF present. I do see that carbon-oxygen bond, which is a 2.5 minus a 3.5 for a 1.0. So I've got a polar bond. So there is one instance where it is a dipole-dipole. And I do see that there is an HF, HO, HN present, which this time I'm going to circle the one that's present. So that tells me that there's also hydrogen bonding. So I see that the molecule on the left has a lot of LDF and a little bit of dipole-dipole. The molecule on the right has LDF, dipole-dipole, and hydrogen bonding. So that means that the molecule on the right has a lot stronger set of intermolecular forces of attraction. And because it has that stronger set of intermolecular forces of attraction, it's going to become more difficult to overcome those forces of attraction, which is why there's a lot more energy. So here's my explanation. The larger boiling point of CH3CH2OH is because the intermolecular forces of attraction, I'll just write IMF because that's easier, are stronger than the IMF of CH3OCH3, meaning more energy needs to be added for that liquid to boil. And the intermolecular forces of attraction to be overcome. So that's essentially the explanation that we're going to be looking for. And I'm going to give you an opportunity to pause the video here and copy everything down. Okay, now that you've copied everything down, we're going to take a look at a different molecule or set of molecules. Here I have CH4, and here I have H3CH3. So I'm going to take a look at the structure, at the chemical formulas here. Here I have CH4, and here I have C2H6. So this time they're not the same, but there is a reason why the CH3CH3 has a larger boiling point, even though it's still negative compared to the CH4. So I guess let's take a look at which intermolecular forces of attraction are present. So I know that this is a covalent compound. Which tells me that automatically there's LDF present. Clearly I'm doing this at school, so sorry about that. It is a nonpolar compound. So that means that's the only intermolecular force of attraction that's present. So there is no dipole-dipole. And no HF, HO, HN. So that's it. Moving over to the other one, I have the CH3CH3. Again, it's a covalent compound. Which means I'm going to have LDF no matter what. It also happens to be nonpolar as well. And there's also no dipole because there's no polar bonds. And there's also no HF, HO, or HN. So they're both LDF. So why does one have a higher boiling point than the other? And the reason is, in this case, it's a bigger molecule. With more electrons. So because it's a bigger molecule with more electrons, it has a larger LDF, which means it's going to require more energy to overcome the intermolecular forces of attraction. So we'll write that down. So the molecule is larger, the LDF is greater, and more energy, if I can spell, ER, is required to overcome the intermolecular forces of attraction. All right, I'll give you an opportunity to pause that video now and copy that down, and then we'll go on to the next video, our next example. Okay, here we have an example where we have, again, the same, very similar molecule, but not quite the same. So we have a C2, we have an H6 and an O2, and we have a C3, and we have a 1, 2, 3, 4, 5, 6, 7, 8, H8O. So molecules are different, but the boiling point is significantly higher for the one on the left than the one on the right. So let's take a look. Here we have a nonpolar, or I lied, we have a covalent compound. So that tells me LDF is present. It looks nonpolar, but it actually is polar. Because of the carbon-oxygen bonds right here. So that tells me it's going to be dipole-dipole. And because there is HO present, tells me there's going to be hydrogen bonding. Okay, and then over on the right-hand side here, I have very similar. It's covalent. So that tells me it's LDF. There's a polar part of it. So that means there's right here, it's a polar bond. So that tells me it's going to be dipole-dipole. And there is an HO, so that tells me it's going to be hydrogen bonding. So at this point, everything is the same, except the fact that it's hydrogen bonding times 2, because right here. And so because there's 2 hydrogen bonds and 2 dipole-dipole situations, what that tells us is that it requires way more energy to be added in order for it to boil. So I'm going to put that into words for us. In this case, the 2 hydrogen bonds and dipole-dipole create a stronger intermolecular force of attraction that will require more energy to be added to overcome the intermolecular forces present. Okay, so that's it. Hopefully that made a little bit of sense. If not, we'll definitely touch base on this again on Wednesday because we don't have school on Tuesday, and we'll see how things go. You do have to definitely make sure you finish worksheet number 1, which is a 1-sider, and you definitely should work on worksheet number 2, which is a 2-sider. We will see how things go. Those are technically going to be due on Thursday, but you should probably get going on them now. You should have plenty of class time to work on them, and I will definitely see you on Wednesday. Have a great day.